Hello, welcome to this session. In this session, we will start looking at the drawbacks of analog charge pump PLL, and as a solution to the problems in the analog charge pump PLL, we will introduce digital PLL and look at how we design digital PLLs. Okay. So, the analog charge pump PLL, which now we are so used to, is something like this. You have PFD, charge pump, followed by loop filter. For easier analysis, we will use only type 2 loop filter here, and this is VCO, divider and feedback like this. Okay. And you have your reference here, and this is your output. Okay. So, the problems with the analog charge pump PLL are as follows. Here, when you design a PLL in a given process technology, let us say 180 nanometer, and when you would like to port, when let us say same frequency is needed in 65 nanometer technology, this kind of PLL, okay, is difficult to port from one technology to the other technology. So, let us look at the blocks which you can port. So, the output frequency is the same, okay, but what happens is your technology changes. So, when your technology changes, your PFD, which consists of NAND gates and other combinational logic, that is easy to port. Your charge pump, which consists of your current sources. Okay. Now, this charge pump, I will just show you the example. So, what happens is when you have a charge pump in a given process, which is like a switched current source, and when you change this from 180 nanometer process, this is not 180 volts, so let me just write it, this 180 nanometers to when you put this charge pump to 65 nanometer for example. Okay. Then here what happens is your minimum length which you are using here as 180 nanometer, this particular length actually can be 65 nanometers. Okay. You can still retain it 180 nanometers, there is no problem in retaining 180 nanometers, but your the benefit of going to a lower process is the smaller area for the same block. So, this problem will come. So, when you change it to 65 nanometer, the charge pump relies on the fact that the top current source and the bottom current source, they are exactly matched, and it is a known fact that as you go down the channel length, or as the channel length reduces, the matching which you will find between these devices, right, the up and bottom current source, that will become more and more difficult if you are just reducing the length. Okay. They are like the short channel effects. So, the idea is that the charge pump operation relies on the output current or an analog value, and as you scale down the process, what you will find is it is difficult to maintain the matching between the top and bottom current sources for the reduced channel length. And if I say even in the reduced technology of process node, if I am using the same length, then what is the point of scaling the charge pump down to the lower process? Okay. That is something which you can always give as a counterintuitive, but a counter to this. Now, the thing is that this charge pump has the issue. The other thing is the VCO. If you have an oscillator ring VCO which is operating at 1.2 gig in case of your 180 nanometer, and you want to implement the same oscillator in your 65 nanometer process, the oscillator will also scale. Okay. But in both the cases, for the oscillator and the charge pump, for oscillator and charge pump, okay, the supply voltage reduces, supply voltage reduces the headroom available for current sources in these blocks. Okay, the voltage headroom for current sources. Now, for oscillators, it is not a problem, okay, because the device length reduces, so the maximum frequency typically increases. So, achieving the same frequency is not a problem in the lower process, but the problem is with the current charge pump. And the problem is, one thing is you say, okay, I am not getting the matching, and if you are not getting the matching, you would like to, with a single transistor, you would like to increase the output impedance looking in by having a cascode. You can't have a cascode because the supply voltage is limited, so charge pump faces a real issue. So this is the problem with the analog charge pump based PLL as you put the process. Other problem is that this capacitor which you have, this capacitor occupies a lot of area for a good output jitter. Okay, so the capacitor area is, I will say, it is a problem. Okay, why it is a problem? Because as you go down to a lower process, we all know that lower technology nodes, they are much costlier, and you are implementing the same kind of MIM capacitor, metal insulator, metal capacitor, whether it is 180 nanometer or it is 65 nanometer or maybe 28 nanometer or something, right? So the capacitor density generally does not increase as you go down to a lower process. The capacitor area is large, and when the capacitor area is large, actually it is going to cost more as you go down to a lower process. So area of the capacitor remains fixed from 180 nanometer to 65 nanometer, but at the same time the cost increases. So this is not a good idea as such. Okay. Now this capacitor, the metal insulator, metal capacitor, MIM capacitor, which we normally use in a CMOS process, okay, it has a typical density of, you can say, 2 femtofarad per micrometer square. And you think about it, if you are implementing 100 picofarad of capacitor, what problems you will face, right? The area is going to be large. So just a typical example, I want to implement 100 picofarad by using this 2 femtofarad, right? 2 femtofarad per micrometer square. So the area is going to be 50,000 micrometer square. Okay, so 50,000 micrometer square, you can say roughly it is 220 to 220 micron area. This is okay, 100 picofarad is not that much. At many a times you would like to have even much larger capacitor for better phase noise at the output. Okay, now the substitute for this capacitor is using a MOSFET. So in place of using MIM capacitor, metal insulator, metal capacitor, someone say, okay, if the density is a problem, I am going to use a MOSFET which also scales down with the process. This particular MOSFET has a real problem that this MOSFET comes with a current leakage. Okay, and this, what is this I leakage? This is the gate current leakage. Okay, so I'm just modeling the MOSFET used as a capacitor with a leakage current. Okay, this is your loop filter which you have. Now, if you have this current leakage, well, what is the problem? Well, the problem is, if I say that I have a constant gate leakage current here, IL. Okay, writing leakage is too much. So I will write this I leakage. So now you know that during your up and down pulses in the charge pump, this I leakage is present everywhere. So if this I leakage is present everywhere, you can think about it that this control voltage will always keep on reducing. So if I think that I am going to have these overlap pulses as overlap between up and down such that it locks to a zero phase offset, right? Ideally this should happen, but what happens is this I leakage current comes in and your VC keeps on dropping. If VC keeps on changing, V control also keeps on changing. So I'm just showing you that, okay, there's a constant current I leakage which is present all the time. It may be very less, okay, but the thing is, as your capture area increases or the capture is large, your leakage current is also large. So this is I leakage current. It is always there. So your V control voltage will always keep on decreasing or increasing. That depends on the leakage current. Okay, is it positive or negative? So just an example I am plotting that your voltage always keeps on decreasing. And if that this thing happens, then you know that it is not possible for the PLL to be locked in this state where your control voltage is always varying. So this will not happen. And if this doesn't happen, what will happen is that you will have a phase offset in a real case. So if I am going to have a phase offset, my up and down pulses will be like this, okay, and you are going to compensate your gate leakage current with phase offset here. Okay, what will happen then? Your just a change here. During this time, you will increase this potential every time, and during the other time, you are going to reduce the potential. Your IL remains fixed. The only thing is you get extra current from the charge pump during the time when up is high and down is low. So this thing is going to happen, and this kind of control voltage, right, VC and similarly your VCR, this kind of control voltage will increase the reference per value at the output. Okay, so using a MOS capacitor in place of a MIM capacitor is surely not an option, because that gives a lot of offset at the input of the PFT, which is going to increase the per value at the output. Okay, so this is an issue. So what we can say is, in summary, the analog charge pump PLLs are difficult to port from one technology to other technology for multiple reasons. One, your charge pump, the matching between the up and down current sources becomes actually that matching goes bad as you go down to a lower technology. Other thing is your capture area which you are having, that particular capture area is a lot. It costs more in a lower technology nodes. MOS capacitor is not an option, okay, because of the gate leakage current. And your charge pump also has a problem with the reduced voltage headroom to operate while still maintaining the matching between the top and bottom current sources. Okay, so this is the problem we have. So we are going to address these problems one by one. The first one, let us look at it, the area for the capacitor. So how can we, this is the problem which we need to address for loop filter capacitor. Okay, the other one which we are looking at, the charge pump issue, we will find that while solving the problem for the area for the loop filter capacitor, that problem will also get solved with some additional inputs. So here uh, the idea is that this particular block, the charge plumb plus your loop filter capacitor, is implementing at V control. The transfer function which it is implementing is this. V control of S in Laplace domain is equal to ICP, let us say whatever charge pump current you are having, ICP times R plus ICP times 1 over SC1. Okay, now we are going to replace this S here with its digital equivalent using bilinear transform. Okay, and what is this bilinear transform, by the way? Bilinear transform is S divided by 2 over Ts, which is the sampling rate, into 1 minus Z inverse divided by 1 plus Z inverse. Okay, if I do this, then ICP times R plus ICP times Ts divided by 2, 1 plus Z inverse divided by 1 minus Z inverse. Okay, so ideally speaking, what we have done is we have just converted this analog transfer function to its digital equivalent. Okay, for frequencies much lesser than the sampling rate which I am using to implement this digital transfer function. Okay, for F, frequencies much lesser than, you can say less than your sampling rate, these two transfer functions will have the same input to output response. Okay, so now I will just write this in terms of V control from Laplace domain. I will write in terms of Z domain. I have the transfer function ICP times R plus ICP Ts by 2 to C here. So C1 is, I forgot that, C into 1 plus C inverse 1 minus C inverse. Okay, this particular transfer function can be implemented using two paths. One, I will write V control of P of Z, and the other one is V control of I of Z. Okay, so ideally speaking, this V control P of Z, if you think about it, what is this transfer function doing? V control of S, this is ICP times error. So whatever your phase error you have at the output of the PFT, right? Whatever your PFT output is, that PFT output, the phase error, PFT detects the phase error and your PFT output is getting multiplied. So this transfer function, V control of S, can be written as your, let me come to the block, because this is a standalone value where I am just considering this loop. Okay, what I am doing here is I am saying this is ICP and this is V control. Okay, so this particular analog transfer function is now represented by a digital value, digital transfer function, where your ICP is the input, okay, and your V control of Z is the output. That's what you see here. Okay, now to simplify this a little further, okay, I know that this charge pump which I am having is controlled by, this is ICP, right? This is controlled by phase your PFT output. Okay, whose gain, so this PFT output, you have a phase error at the input of the PFT, you get up and down pulses. Okay, so from PFT block to your charge pump block, so you have a phase error at the input, and this is like the voltage which you have. Okay, so VPD you have. So from your VPD to your charge pump output, the gain which we are using is ICP. So what I am trying to do here is the following. These two are in standalone blocks. Okay, so now I will write V control of Z is equal to your ICP times VPD is again there times R. VPD is your phase detector output, and similarly it's not a big difference here. The only thing which will happen is that I have to take the VPD out. Okay, I am writing everything in terms of G domain. So this is the transfer function which you can say I am implementing from our PD output to our control voltage. Okay, so the previous expression which we wrote here, this one for a standalone this circuit. Now when we bring our PFT and charge pump together, this is what you get. Okay, now come back to this and look at it that from PFT output, somehow, we do not know how, but somehow we are converting this phase detector or the PFT right now, that is a voltage, but somehow we are saying that we are implementing this transfer function to V control, which is controlling our VCO. So whether this function can do it or not, that is something which still needs to be checked. So let us now just take this function as such as YYZ divided by X of Z as ICP times R plus ICP TS by 2C1 into 1 plus Z inverse by 1 minus Z inverse. Okay, this transfer function I am going to divide in two parts, one H proportional of Z and other H integral part of Z. Okay, why integral part? Because there is 1 minus Z inverse which acts like an integrator. Okay, so if you look at H proportional of Z, it is telling Y of Z by X of Z. Okay, so H proportional is Y proportional of Z, this is just Y in the proportional part, is equal to ICP times R, which I can call as K. Similarly, H integral of Z is equal to Y integral of Z by X of Z, and this is equal to ICP TS by 2C1 times 1 plus Z inverse by 1 minus Z inverse, which is Ki into 1 plus Z inverse by 1 minus Z inverse. So this is the transfer function which you have. Now these two things, right, it is what you are looking here as Z, which is like a discrete in nature. The block diagram for this, okay, can be that I give X of Z, and from X of Z I have a proportional path with Kp. Okay, it gets added up. I will use an adder here right now, and then this particular transfer function which you are seeing here, K I divide by 1 minus Z inverse into 1 plus Z inverse. For simplicity, let's ignore this part. Okay, if you want, we can also implement this. Just ignoring the numerator, that's the 0 frequency which you have. What we are doing here is we are having a Ki, and then on the top of the Ki, we are integrating. This is just a block diagram by Z inverse here, like this, and it gets added up here. So this is a Y of Z based on X of Z here. Okay, now just look at it. This is Y proportional and this is Y integral. So what is Y integral? Y integral of Z is your Ki times X of Z, right, plus your Z inverse times Y of Z, which relates to Y integral of Z by X of Z as Ki by 1 minus Z inverse. Okay, so I told you, yes, we are ignoring this part. This is just a 0 which we have. Later we will find that it can be neglected, okay, while you are implementing it, and many other things will come which will add to this stuff. Okay, so the transfer function which you see here now, this is Kp and Ki. So let us just look at it. The overall transfer function is Y of Z by X of Z is Kp plus Ki. Okay, if we take this, then you have 1 plus Z inverse by 1 minus Z inverse, right? And this shifts to 1 minus Z inverse Kp plus Ki, okay, plus Ki minus Kp times Z inverse. Okay, so you have a 0 and you have a pole, right? The pole as per this Z transfer function is at Z equal to 1. Okay, and Z equal to 1 here is like, by the way, Z is replaced by e power s ds, right? So Z equal to 1 is what we are saying is that s is equal to 0. Okay, so that's what we have. Now, given this transfer function, what the exact value we are going to choose for Kp and Ki, let us, that is still something to look at, and we will see that. But before that, the question is how you are going to implement this, and this is digital block which Z inverse is like a delay in the transfer, delay in the value. So this block is going to be implemented using digital accumulators as, so I will just plot this first and then replace each of these blocks with their corresponding digital counterparts. Okay, so here just paste this. Okay, I think putting it here is a better option. Okay, so first this accumulator which you are seeing, what you will see here is that this I goes to an accumulator which is normally represented by this block, okay, Ki, and then you have this Z inverse. Similarly, this one you can have a similar block here. Okay, it goes here and this goes here. So this is your Y of C. Okay, this is Y proportional, this is Y integral. This A1 and A2. A1 and A2 are digital accumulators. Now, if they are digital accumulators, okay, depending on what speed you are clocking them. So normally, all these accumulators are clocked at a certain frequency, and in this case, this is your sampling clock period. So Fs, normally here it is equal to your reference frequency. Okay, these are all digital accumulators. Now think about it, whether you implement this digital accumulator or the digital loop filter in 180 nanometer, or you are going to implement this in 65 nanometer. These things will remain the same. There is no problem in porting from one technology to the other technology. Actually, as you go down lower to a lower technology node, in that particular case, you will find that implementing this is more power. You will save actually more amount of power. Okay, so now the thing is that this particular digital accumulator, they will operate at a clock. That is one thing. Other thing is, now you are having a digital accumulator, so they need bits at the input, and the output is also going to be in bits. 1 0. You are implementing an accumulator, and your digital filter, this is like a digital loop filter, you will have to feed in the bits and get the bits out. Okay, what was PFD giving earlier? PFD was giving us analog, the phase error. So if you have any phase error at the input, PFD was giving the difference between the timing difference. Now that timing difference has to be converted into bits. Okay, so now given this loop filter, if you are going to use this particular loop filter, which is helping you to replace the loop filter capacitor in the analog PLL, you have to, so let me just remove this part now. This is the loop filter which we are adding. So what I want to do is, I want to convert the phase error from PFD in bits form. Okay, so I still have the reference clock and voltage, that they remain the same. So I need a block which converts the timing information between your reference and your divided clock to digital bits. Okay, and that particular block is called as TDC. It gives you the information about the phase error in bits. Okay, similarly, the output of the loop filter is digital. This dash just tells you that there are number of bits, how many which we still do not know, but this is like n bit or m bit you can have depending on how many bits information you have. Okay, and this has to be converted to the oscillator. So I have an oscillator here which normally works on voltage. Okay, you need this V control voltage to change the oscillator frequency. So I have to convert these bits to V control. And if I have to convert these bits to V control, what I need is a DAC, digital to analog converter. Okay, and then you have this VCO frequency, VCO output. Well, VCO output remains same. This is divided by N. This is your basic digital PLL. Okay, here TDC is time to digital converter. It converts the timing error or the phase error which you have at the input of PFD earlier, the reference and the feedback, right? Divided signal or feedback signal time. It converts that error into digital bits. That is what TDC does. Okay, and your DAC converts the digital output of the loop filter to analog control voltage, which are needed for the oscillator. Okay, so using TDC, DAC, and this whole block is normally called as digital loop filter, DLF. Okay, we need to see how we can use both of these blocks, all these blocks actually, to make our PLL work better or the way we want. Okay, thank you.